Hi everyone, I am Nivedita Bijlani from the Center for Vision, Speech and Signal Processing at the University of Surrey. We are very happy to be presenting our work at BMVC. In this paper, we propose a novel unsupervised approach to anomaly detection in noisy, multivariate time series data obtained from sensor-based remote health monitoring. We combine the strengths of distance-based anomaly detection and graph learning for streaming data. Sensor-based monitoring is used in a variety of industry, urban, and healthcare settings. Drawing insights from sensor-based data enables us to analyze temporal patterns and detect adverse conditions on an ongoing basis with minimal intrusion and low cost. The idea is to intervene early when problems occur. However, real-world sensor data is characterized by noise, multivariate data, absence of reliable labeling, data drift, and lack of periodicity. There is also a lot of variability in operating environments. Current work on anomaly detection in these settings is challenged by computational complexity, low scalability, low interpretability, or a lack of a continual learning strategy. So in this paper, we focus on fast, lightweight, self-supervised anomaly detection for noisy, unlabeled time series data. We propose a novel graph-based approach for temporal anomaly detection that works on time graphs generated from the contextual matrix profile. The learned graph embeddings encode the anomalous nature of a time context. Our approach is domain agnostic and can work with time series data from video, image, audio, or any other modality. We evaluate our approach on two sensor datasets collected from health monitoring of people living with dementia. The contextual matrix profile, or CMP, is based on a state-of-the-art distance-based anomaly detection technique called the matrix profile. It computes the pairwise nearest neighbor distance between time contexts. A time context is a block of time series subsequences to consider as a single time unit when comparing for pairwise distance and represents one cell in the figure here. In this way, we can denoise the time series and look at how far each context lies from every other. As we can see, the CMP offers a visual thumbnail of the entire time series. Anomalies can be identified here as the green bands, where the specific time context is considerably further from most of the contexts earlier in time. Interestingly, the distance matrix is also a natural candidate for graph generation. A multi-dimensional time series can be converted into a multi-channel CMP, which in turn can be represented as a set of evolving time context graphs. Here we see a star graph where the central node represents a single time context connected to previous time contexts. The node feature vector contains the feature-wise context to context distances. Graph learning on this set of graphs produces embeddings that can be used for downstream pattern detection tasks, which was not possible with the CMP alone. This figure shows our graph representation learning pipeline. We have used the feature-stacked CMP to create time-evolving graphs. As we want to work with unlabeled data, we provide a self-supervised learning objective to the GCN, which is to compute the distance between a pair of input graphs based on the Euclidean distance contained in the CMP distance matrix. The intuition is to evaluate the anomalous nature of a time context in relation to the distance to preceding time context nodes. So this will help generate embeddings based on graph distance, where a large distance represents an anomalous time. We then take the difference between successive graph embeddings and apply moving average based thresholding to identify the anomalous time contexts. In addition to using self-supervised GNN, which we'll show next, we also evaluate existing graph outlier scoring algorithms on top of these time graphs. This diagram explains how the self-supervised GCN works. Consider the training pair example 1. These correspond to time contexts 9 and 14. The target for this input pair is the Euclidean distance between the CMP matrix up to context 9 and up to context 14. Given that the graphs have quite a simple star structure, we therefore only require a single layer GCN or graph attention network to aggregate the outer node features and obtain the embeddings. The network is trained to compute and maintain this graph distance. In addition to the self-supervised GCN, we apply 4 different graph outlier algorithms to detect anomalies. The MLP autoencoder uses a denoising autoencoder to extract latent features from input data via nonlinear dimensionality reduction and reconstructs the original data. The GCN AE consists of a GCN encoder and an inner product decoder applied to the latent variables. Dominant is a GCN-based autoencoder that models node interactions with layers of nonlinear transformations. One-class GNN is a hypersphere learning framework that combines the node representation ability of GNNs with the hypersphere learning objective to detect anomalies. The data for our experiments comes from the Minder research study from the UK Dementia Research Institute. Minder is the platform that enables the workflow of collecting multimodal sensor data from homes of people living with dementia. It allows AI algorithms to detect and predict events and patterns related to their activity or behavior. We focus on passively collected household movement data from 65 participants who had agitation or fall events in their timeline. This is a total of 183 adverse events over a total of 18,710 days. We compare our graph models relative to the multidimensional CMP alone, as well as 3 other modern, fast, lightweight methods in literature: angle-based outliers, copula-based outliers, and LODA. Each model is then evaluated based on average recall, participant-specific recall, and alerts raised. Our experiments on these 2 real-world datasets shows that the GNN was able to outperform the vanilla CMP and other methods. It showed higher recall, lower alert rate, as well as top participant level validity. The hyperparameters for these experiments were tuned on a separate 15-patient dataset of urinary tract infection events. In conclusion, the CMP powered by GNN represents a new generic approach that combines graph-based machine learning with distance matrices for pattern and anomaly detection. Graph learning was able to outperform the CMP and other SOTA methods for adaptive anomaly detection. Time context graphs are generalizable, scalable, and domain agnostic. Graph embeddings can be analyzed for temporal patterns, clustering, or used for downstream tasks such as anomaly classification. Our pipeline is flexible, and each part from feature definition to anomaly thresholding can be adapted to the application at hand. But importantly, operational monitoring teams can benefit from interpretability, which can be traced back to the CMP distance matrices. The remote health monitoring in healthcare is only one application. This idea can be easily applied to computer vision. For instance, we could generate the CMP from image representations extracted using a CNN. Our future work will explore a number of improvements: graph attention and the use of sparser graphs that can help amplify anomalousness, the use of contrastive learning, an end-to-end learnable framework from feature extraction all the way to anomaly detection. And we can also think of extending the approach to semi-supervised and supervised learning, where some annotation might be available. Thank you so much for watching. Please come and see our poster at BMVC. We look forward to seeing you there.